So our next topic is liquefaction of gases. Liquefaction of gases. See, to understand about liquefaction of gases, let us begin with enthalpy. Enthalpy for a system is equal to U plus PV. Here, here U is the internal energy of the system and PV is the product between pressure and volume. And actually this expression is the macroscopic expression. Macroscopic expression for enthalpy. Okay. And microscopically, this equation will be modified as like this. Is H equal to for this is PV is equal to N of T. From that you will get PV equal to 5 by 2 N K suffix B T. So we can use the value of PV as 5 by 2 N suffix N K suffix B T. Then for internal energy, N squared by V into B K suffix B T minus 2A. So this is the microscopic expression for enthalpy. Here 5 by 2 N K suffix B T, this factor indicates temperature because it is equivalent to kinetic energy of gas molecules, so which is nothing but the measure of temperature because both are equal. In the case of three-dimensional, there is translational gases with having translational motion, you can use 3 by 2, whereas for if you include vibrational and rotational degrees of freedom, then it will be modified as 5 by 2 N K suffix B T to represent temperature of a molecule having gas molecule with 3 different degrees of freedom. So this represents PV, and internal energy is represented by this factor N squared by V into B K suffix B T minus 2A. Here what are these? Of course H is enthalpy and N is total number of gas molecules. N means total number of gas molecules. And K suffix B is Boltzmann's constant, and T, you can consider T is the T suffix I or initial temperature. This T is initial temperature. Maybe this T is final temperature after expansion. So this T is initial temperature before expansion according to Joule-Thomson Kelvin experiment, and this one is final temperature after expansion, temperature of gas. So what are the unknown factors for A? A is measure of molecular strength of that is force of attraction between gas molecules. This is a measure of force of attraction between air molecules, and V is volume. V is volume of gas molecules. So now we will move on to, so in this expression, H is throughout the experiment, H is according to Joule-Thomson's experiment, H is constant, that is enthalpy is constant. So the experiment for the liquefaction of gases will be conducted under adiabatic condition, as well as under isenthalpic condition. So adiabatic means no heat enters or leaves the system, and isenthalpic means del H is 0. It means H is constant. Here H is constant. So this experiment for the liquefaction gases will be conducted under adiabatic as well as under isenthalpic conditions. So H will be constant. Okay. So in this equation, this part is the most deciding part. B into K suffix B Tf minus 2A is the most deciding part to decide the fate of this expression. Also keep in mind, throughout the procedure, H remains constant, other parameters may change. Okay. So I just to understand how liquefaction takes place or how temperature is reduced after expression, just introduce 3 cases. Case 1. In case 1, if B sub P, B into K suffix B T F minus 2A, if this factor is equal to 0, it means B into K suffix B into Tf is equal to 2A. If both values B, K, T is equal to 2A means there is molecular attractive forces are equal to the temperature, that is temperature rise after expansion. Then in such situation, this factor becomes 0. When this factor becomes 0, then this equation, constant enthalpy equation, is reduced as 5 by 2 N K suffix B T plus 0. Keep in mind, H remains constant, but the initial temperature of gas is not affected even after expansion. That is what we have to understand. So initial temperature is not affected because no factor is added, new factor is added or subtracted. So therefore, for case 1, temperature remains constant. This is according to Joule's earlier experiment. So according to Joule's earlier experiment, initial joules highly written dt by dp equal to 0. It means T1 equal to T2. So their initial and final temperatures are same. So that is what Joule's prediction. So this resembles Joule's prediction. So since initial and final temperatures are same, temperature remains the same. So this critical point is said to be inversion temperature. This temperature is said to be inversion temperature. So at inversion temperature, the temperature remains same even after the gas is allowed to expand. At a particular pressure and temperature, it remains same. So dt by dp equal to 0, or under isenthalpic condition, that is mu suffix Jp, Joule-Thomson's coefficient dt by dp under adiabatic and isenthalpic condition becomes 0. So there is no change of temperature. This is case 1. And in case 2, greater than B case of Bt final is greater than 2A. In this case, since this factor is greater than molecular forces of attractive forces, so now the change in this entire part is changing entropy. N squared by V into B k sub x bt minus 2A is change in entropy. So now change in entropy, in the previous case 1, change in entropy, change in internal energy, U. Change in internal energy is 0. In the previous case, for case 1, change in internal energy is 0. So change in temperature is also 0. Whereas in this case, there is change in entropy, change in internal energy is positive. That is, it increases. This factor increases because B k suffix B into Tf is greater than 2A. So naturally this part increases, magnitude of this part increases. So change in internal energy increases positively, and so temperature also rises positively. So it means after expansion, temperature of the gas molecules is increased. It starts to increase. Okay, because some force or magnitude is added with this part. So naturally temperature is increased. So T final temperature will be greater than initial temperature. So dt by dp is greater than 0. It increases positively. Or T1 minus T2, or T2 minus T1 is not equal to 0. So Boltzmann Joule-Thomson coefficient mu suffix Jt equal to is greater than 0. And if you look at the third case, so it is also not usable. So that is we want liquefaction. We have to lower the temperature or we have to cool the temperature of gas. But in this process of case 2, when gas is allowed to expand at a particular pressure and temperature ranges, what you get, changing in internal energy positively and change in temperature also positively increases. It means temperature of the gas increases after expansion. So it is also not helpful for liquefaction. Case 3. Now, B suffix Kb T is less than 2A when molecular attractive forces dominates the final temperature after expansion. So in this situation, this portion becomes, we get a minus sign because 2A dominates. So when it gets a minus sign, so the initial temperature, this part also become, there is change in internal energy will be minus, that is decreases. Internal energy changes negatively. Okay. Internal energy changes negatively. So in this way, temperature of final temperature is smaller than the initial temperature, or the temperature is reduced. Temperature is reduced. That is T2 minus T1 is equal to not 0. So dt by dp so Joule-Thomson coefficient dt by dp is less than 0. So now temperature starts to decrease at these conditions of pressure and temperature. So these are the different cases. So this case is helpful, case 3 is helpful, that is this condition is helpful to liquefy gases. So Joule and Thomson-Kelvin experimentally proved all these 3 cases for different combinations of pressure as well as temperature by allowing gas molecules to repeatedly expand. So when they conducted multiple experiments by varying pressure and temperature, they got a curve like this, pressure in the x-axis and temperature in the y-axis. They obtained different points. And when connected these different points of temperature versus pressure, they got a parabolic curve. And at one point, it is pressure temperature is maximum, and at which it corresponds to inversion temperature, T inversion temperature, that is case 1. What is case 1? B, K suffix B, T minus 2A equal to 0. At this point, B, K suffix B, T is equal to 2A. So at this point, both are equal. So change in internal energy will be 0. Change in internal energy will be 0. And also change in temperature is also 0. So at this point, case 1, you can use case 1 here. Change in internal energy is 0, change in temperature is also 0. And right hand side of this curve, from the inversion point, right side of this inversion point, what you get is this is case 1. Case 2, that is D K suffix B T is greater than 2A. So in all these points, liquefaction is not possible and the gas, that is gas temperature increases after expansion. So gas warms. After expansion it warms. And the points left to the inversion temperature, inversion temperature belongs to case 3, where B K suffix B T is less than 2A, is less than 2A, or the temperature change in temperature is negative and change in internal energy is negative. So gas cools. The points left side of this inversion point, now the points of pressure and the temperature, it cools, gas gets cooled. So for at this point, dt by dp is 0. dt by dp equal to 0. And for all these points right to this inversion temperature, dt by dp is greater than 0. And for all the points left to this inversion temperature, dt by dp is less than 0, means gas gets cooled. So liquefaction takes place in this zone, and in this zone gas is being heated. So we want only this zone. So every gas molecules have their own inversion temperatures, maximum inversion temperatures. So based on its molecular attractive forces and the potential energy, based on the difference between kinetic energy and the potential, based on the balance between kinetic energy and internal molecular force of attraction, every gas molecules have their own inversion temperature, maximum inversion temperature. So if you can plot a curve for different gases, like I just roughly draw these curves for different gases just to make you understand. One, two, three, four, five, six, seven, eight. So in this case, here, this is for helium, hydrogen. Third curve is for air. Fourth one is for nitrogen, oxygen, CO2, CH4, and argon. So for different air molecules, if you plot between temperature and pressure, these curves. So as I already told you, maximum inversion temperature is different for different gas molecules. So imagine that you get a maximum inversion at here for helium, for hydrogen it is at here, for air it is the case of oxygen. So these points represent different inversion temperature for specific gases. So for CO2, it's 1500 Kelvin. For methane, it is 939 Kelvin. For argon, it is about 764 Kelvin. And in the case of oxygen, 714 Kelvin. For nitrogen, 664 Kelvin. For air, maximum inversion temperature is around 604 Kelvin. For hydrogen, it is 200. And in the case of helium, it is 45 Kelvin. So 48 Kelvin is the maximum inversion temperature for helium. So it means hydrogen, so if maximum inversion temperature of hydrogen is 45 Kelvin, means above 45 Kelvin, hydrogen warms even after expansion. But only below 45 Kelvin, it can be cooled. Similarly, every gas molecules have their own inversion temperature or inversion points. In the case of CO2, it will be cooled even at higher temperatures, at 1500 Kelvin. If the temperature is above 1500 Kelvin, then it will be warmed. If it is allowed to, if the temperature is below 1500 Kelvin, then it starts to liquefy or cool. So these are the different inversion temperatures. And if you connect these locus points of inversion temperatures, you will get a curve. So this curve is said to be inversion curve. This curve is said to be inversion curve, and the pressure and the temperature points left side of the pressure of this inversion curve, cooling takes place, and pressure and the temperature points right of this inversion curve, gas molecules warms when allowed to expand. And the slope of this curve, slope of these parabolic curves is said to be Joule-Thomson Kelvin. Joule-Thomson Joule-Thomson coefficient. Slope is Joule-Thomson coefficient, so it is dt by dP under isoenthalpic and under adiabatic condition. So this is how we have to liquefy the gas molecules. These are the basics, very fundamental concepts behind liquefaction of gas molecules. And basically there are three different methods of liquefaction of gas molecules. One is Faraday's method, and the second one is Lind's method. Third one is Claude's method. So these are the different methods used for liquefaction. And in the case of Faraday's method, gas molecules having higher temperature of inversions can be liquefied. For example, CO2, which is having 1500 Kelvin, can be liquefied. And also chlorine, then SO2, all these gases having maximum higher inversion temperatures can be liquefied. And in the case of Lind's and Claude's method, usually air is liquefied. So these methods, Lind's and Claude's method, uses the basic, it is based on the experimental setup of Joule-Thomson Kelvin's experimental setup and theory. And here, Lind's method and Claude's method uses Joule-Thomson Kelvin's, basically uses Joule-Thomson Kelvin's experiment. And in this case, more liquefaction is possible by means of Claude's method, because in addition to Joule-Thomson's experimental idea, Claude's method, they used additional work by means of adding a piston. So on the piston, additional work will be done in order to move the piston. So it will further reduces